We're going to start by looking at sigma notation. And you've probably seen this in tests, the big Greek letter sigma. We're going from I equals 1 to some number n. These are our upper and lower sums. And say if this is our function, just some a sub I, this just means that I'm going to take a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. We're just going to add all of those together from 1 to whatever n happens to be.
What does that say? Gout?
What? A sub n. Dot, dot, dot.
That looks like gout. Doesn't it look like all the way down? Yeah.
Classes
It's a medical
Do your feet hurt?
No, I thought that's what it looked like you wrote. I didn't understand.
Okay. This is called our index of summation. Sometimes it'll use I, sometimes it could use J. That would be your index of summation. I. It could have J equals, then J would be your index of summation. Notice here, this has an I. That's what's going to change every time. The 1 and the n are the upper and lower bounds of the summation. We're going to start at 1 and go all the way up to n. Let's look at one that we could actually calculate. We're going from I is 0 to I is 4, and my function or the term is going to be I plus 2. That means we're going to have 0 plus 2, plus 1 plus 2, plus 2 plus 2, plus 3 plus 2, plus 4 plus 2. So we could do that one pretty easy. We've got 2 plus 3 is 5, plus 4 is 9, plus 5 is 13, plus 6 is 19. So we could calculate that one without too much trouble. If we go back to one that has an n on top, let's say that we had 1 over n times I squared plus 1. Well, I can't really add all that up because I don't know what n is. But if we wanted to expand it just so that we could see what we're doing, we could have 1 over n times 1 plus 1 plus 1 over n times 2 squared plus 1 plus 1 over n times 3 squared plus 1, and you would go all the way to whatever n happened to be. You can see that could get kind of cumbersome. And another way, this is a differential form of a summation. Again, we'll go to n, and we'll look at this in a few minutes, but that's the differential form. Notice we would substitute the term for whatever, they call it the ith term or the kth term, whatever, based on what you substitute right there. Yes, ma'am? N squared plus 1. It's just finishing out that pattern. This would be f of x to the first term times dx plus the second term dx plus the third term dx all the way up to whatever the nth term is.
You wouldn't do x to n? It would.
Wouldn't do what? I don't know why that keeps going. So that's just writing it out the long way. You're not going to have to do a lot of that. Sometimes it's easier to add them together. There are some properties with summation that come in handy. One of those is very similar to properties that we've seen before. If we, associative and commutative, if we have the sum from I equals 1 to n of k times a sub I, we can rewrite that with the scalar in front. And a lot of times that's going to be easier to apply that multiplication at the end. Or we also have commutative, if we are adding something together. Okay, you could separate that into two separate summations. Just like we've done with integrals, just like we've done with derivatives, you can rewrite it as two separate summations. Yes. And if I had said k equals 1, then we'd use sub k. Now, there are 4 summation formulas that are very helpful that we can use. I'll move that out of the way. Trying to record this since we've got so many that are out. The first one, if we're going from I equals 1 to n of some constant. So these formulas, these 4 formulas that we're looking at only work when we start with 1, when I equals 1. If we start with I equals 2 or I equals 0, you can't use these formulas. But this is just equal to the constant times whatever n is. So if I were taking the sum from I equals 1 to 5, of 6, this would simply be 30. 5 times 6 is 30.
Is I always 1?
In these formulas, yes. To use these formulas, I has to be 1. Second formula is from 1 to n. I, or say it was just x, that was your function, just x. This is going to be whatever n is times n plus 1 over 2. And yeah, you do need to learn these.
What is n?
Whatever that number is. Whatever that number happens to be.
What is capitalized lowercase? Does it matter?
Same thing.
Same thing.
Yes.
Do these have names? Like,
It's just the summation formulas.
okay.
If we have I squared, this formula is n times n plus 1 times 2n plus 1 over 6.
Over 6.
If you've got n is 100, it's a whole lot easier to use that formula than it would be to try to add all that up. And then the fourth one is if we have the sum, again, from I equals 1 to n of I cubed. This is n squared times n plus 1 squared over 4. We are going to evaluate from from I equals 1 to n, I plus 1 over n squared. And I want to evaluate that for n equals 10, 100, 1,000, and 10,000. Okay, now, I sure don't want to sum all those up. So it would be nice if I could have a formula when I'm finished that I could just plug those numbers into. So that's what we're going to do. We're going to take this summation and we're going to rewrite it in terms of n so that when I'm finished I just have a formula that I can work with. Now we said if n is our upper limit or our upper bound, then it must be a constant. And I can move this n squared to the front. So this is going to become 1 over n squared because it's just some constant n. Notice later because I'm going to plug in a 10 and 100 and 1,000 and a 10,000. So it's just a constant. I can move it to the front. And I'm going to be working with, from I is 1 to n, I plus 1. Right? So we're going to have, if I expand this with the formulas, we said I from 1 to n is going to be n times n plus 1 over 2. And what about that 1? What happens with it?
It goes away.
Doesn't go away. It's a constant, so what do we do when we have a constant that the summation is applied to? Multiply it by n. All right. Algebra here, let's get a common denominator. And I'm going to go ahead and multiply across the top. We have n squared plus n plus 2n all over 2. Is that all right? Does that make sense?
Yes.
Equals 1 over n squared times n squared plus 3n over 2. And I can simplify that. If I factor out an n, then that cancels with one of those. So we get a 1 over n times n plus 3 over 2. Now that's easier to plug in 10, 100, 1,000, and 10,000. So if we use small, make it small. Okay, so we said it was 1 over 2n times n plus 3. If I plug in a 10, what do we get? If you want to use your calculator real quick, you can do that. What do we get if we plug in 10? 13 over 20, which is, what is it as a decimal? 0.65? What if we plug in 100? Well, we'd get 103 over 200, which is 0.515. What if I plug in 1,000? And what if we plug in 10,000? What do you get? 10,003 divided by 20,000?
0.5015.
Okay, so what's happening as n gets larger and larger? What's the sum approaching? 0.5. Could we have been able to maybe figure that out from this?
Yes.
What happens as n approaches infinity? What's our limit? Our limit is 1/2. Ratio of the leading coefficients. So when we got our summation formula finished, we could have figured out what's happening as n gets larger and larger and larger. All right, I want you to try one. Okay, so we have I times I minus 1 squared. You're going to have to multiply that out and then use those formulas to, well, you don't know how to do what? You don't know how to FOIL 1 or I minus 1 and then
So once we
multiply
FOIL
I?
it,
Then you have,
a constant that you move the outside, or is it not?
you will have one constant, but nothing that you can move to the front.
Minus 2i squared plus I.
Is she right?
Yes. So I got
Okay, so what we could do, if you want to separate it out, we can separate it. So it might be a little less confusing. We'd have from 1 to 15, I cubed, minus twice from 1 to 15, I squared, plus from 1 to 15, I. So apply those formulas and see what you get. You will. So what did we get for our sum?
12,040.
Good.
That's something I got.
All right, so here, that's what you should have gotten. Remember, this is going to be 15 squared times 16 squared over 4 minus twice 15 times 16 times 31 over 6 plus 15 times 16 over 2.
So, are you gonna do this in relationship to the area?
Before we do that, I want to show you how you could, another way, because you need to be able to do it with your calculator or with these formulas. Are we okay here? All right. When you're using your calculator, one of your questions is going to say to use the summation capabilities of a graphing calculator to evaluate the sum and then use the properties to verify. So this is the order, and I think hopefully it's going to be on the next screen, but sum, sequence, and I'll show you how to pull those up. And then your function. In this case, our function, hopefully it'll work, x cubed minus 2x squared plus x. And then it's going to ask you for a variable, which is x, and we are going from 1 to 15, and then we are moving in increments of 1. So you'll see all this when it comes up in a minute on the calculator. Hopefully my new app will work. This would be whatever your f of x is,
What is
or possibly even f of x dx. Okay, I'm going to show you how to find it, I hope. Okay, the assignment is going to be on page 261. For those of you that were not here in class, we practiced doing this on the calculator. Let's do 1, 3, 6, 15, 18, and 20. Using the properties here, then you can check it with the calculator. And then 21 and 22. You do that with the calculator and then check it with the properties. Because I want you to be able to do either way. I want you to be able to use those summation formulas that we learned, or do it with the calculator. You need to be able to do it both ways. So read the directions. Read the directions. If it tells you to do it both ways, do it both ways. Okay, we'll talk about the area under the curve and the rectangles on Tuesday. So you've got 10 minutes. So that means sit down and work while you're here. Okay? Or else we can talk about rectangles.